The video you're about to see is a real-time recording made at a live ICRI technical session. It is important for you to realize that the remarks of the speaker do not necessarily represent the views of the International Concrete Repair Institute. This presentation is intended to refresh your memory if you attended the session and to allow you to benefit from the speaker's remarks and from the question and answer period if you were unable to attend. Now here is the introduction to the speaker for this session.
Next, we're going to talk about surface waves and other new testing techniques. We're fortunate to have with us Larry Olson, who's the president of Olson Engineering and Olson Instruments in Denver, Colorado. His firm provides consulting, engineering, and instruments for condition evaluation of infrastructure. He's a registered professional engineer, an ICRI member, and an ACI 228 NDT, non-destructive testing member. They're also one of the exhibitors in the room next door, so if you want more information about Larry's company, you can visit them at their booth next door. Okay. Larry, welcome.
Okay. Thank you, Wayne. Appreciate that. I'm curious, as I start this talk, how many people have seen pulse velocity testing? Hands? Ultrasonic pulse velocity testing. How many people have seen that? How about impact echo? A few more hands. Surface waves. I guess I've got the right topic. I've got probably way more slides than I'll ever get through in half an hour, so we won't worry about that. I put the ones up front I think are most important to you. So with that, we'll just get into some case histories and applications here. Spectral analysis of surface waves. The only technique from one-sided axis that you can sort of, in a physical testing sense, reach in and feel how hard the concrete is. That's the advantage of this technique. It shows you the variation of stiffness with depth. So how does it do it? You have two receivers tapping the concrete, but you're looking at how a surface wave travels between the two receivers. The fundamental of physics is that velocity is equal to frequency times wavelength. I'm not going to dwell on that because with the modern PC technology and digital signal processing, it's basically done for you. If you hit it with a high frequency impact and a short receiver spacing, you get high frequency waves. Say you had a layered system where you had different materials, ages, damage, whatever. Short high frequency wavelengths really only sample the first layer. Longer wavelengths see a combination of velocity that's a function of the stiffness of each of the layers. This is a case history that was done a few years ago. It won a 1994 ICRI project award. Akers International was the main engineer. We were involved in looking at the condition of this dam. It was a 1906 construction vintage Tainter Gate style dam up in Michigan, subject to freeze-thaw damage. How many people know what that is? It's a log chute on a river. They used to bring the logs right through the center. Well, there's some problems with the dam. When you start looking at it, they couldn't tear it down and replace it because they'd never get it re-permitted. They'd lose all the power generation. Just wouldn't happen in today's environment. The upstream side below water, except where the ice damage occurs, was in great shape. The downstream side, which was subject to freeze-thaw and cyclic wetting and drying, had a lot of damage. They'd done a shotcrete repair and hadn't done it well because they had not removed enough of the freeze-thaw damaged concrete before they put the shotcrete on it. So just a few years after that, you had this kind of shotcrete repair. This presented problems from, obviously it wasn't repaired, but from an impact echo testing perspective, it was hard to find spots where there was good bonding and we could test through it. Surface waves did a better job of looking through to see how deep was the damage of the freeze-thaw damaged concrete to be removed and rebuild it on the sound concrete of the piers that remain. So the idea again is hit it, look at the receivers, separated about X and X. So if you start off with half a foot, 2 foot, 4 foot, doubling and so on to see deeper and deeper. So we did start off at about a foot with two receivers. Tap, 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 took the data. Use bigger hammers to see deeper. Some of these walls and abutments were as thick as 7 feet. So we were going quite deep with the surface wave testing. Impact echo, you have trouble seeing much deeper than 3 to 5 feet. with good confidence in the data. Not so with surface waves. Your resolution of small defects diminishes, but you can see through. Literally, we've used it on dam sites for earthquake studies to several hundred feet. So you're not as limited that way. PC-based recording and processing. This shows the data. Here is 1/10 of a foot, and 10 feet of wavelength. This is deeper into the concrete from the surface on an abutment wall. Velocity in surface wave of 0 to 10,000 feet per second. The little white dots show that to about 3/10 of a foot, it was a fast shotcrete, about 8,500 feet per second. Then it got much slower to about almost 2 foot in wavelength before the data showed it getting faster. So this is like a stiff layer over a soft layer over a stiff layer. The open squares are a theoretical modeling that's done to get the thicknesses and stiffnesses of each layer. The end result is inversion, where that's the theoretical modeling. You put in Young's modulus, or velocity of the compression wave or surface wave, Poisson's ratio mass density. These two terms aren't too critical because you normally know them within reason. So we're really looking at velocity, which is related to modulus. Velocity squared is Young's modulus, stiffness. So the end result was to show depth of penetration from the wall into the concrete, 0, 1, 2, 3, 4, and 5 feet. This is the fast shotcrete for about 3/10 of a foot at 8,500 feet per second. It dropped into a very damaged, down to 2,500 feet per second concrete layer. This was the freeze-thaw damaged layer. It went almost a foot deep, and then it was good concrete beyond that. So the investigation was quite useful in indicating how much needed to be removed. When they did the removal process, it showed the damage zone. If it had been something they could have repaired, we could have done subsequent quality assurance of that repair by checking to see how much this zone was injected, say, and did it come back up into the normal velocity range. So it's a useful test, one-sided access, literally, and I try and get people to understand this intuitively. It's like being able to reach through and feel how stiff is each layer in the system if you have a layered system. Okay, part of what's new about it is we just did a project that would have taken twice the amount of time, literally just a half year ago, but we've developed some new equipment. This shows a surface wave bar. It makes the testing much faster. You have variable spacings. You just grab it, press it on the wall. We were testing a concrete wall with void and honeycomb last week. Impact echo and surface waves were done almost at the same rate of testing. First time we've been able to do that. Makes it much faster. We see this surface waves combining with some impact echo for thickness acceptance of pavements and other things where you don't know the thickness, minimizing the amount of cores, but still correlating with cores. I very much believe in cores. They're a good idea, we just take too many of them. Okay, impact echo. This is the one a lot of hands came up on. Hitting it, looking for an echo from a void or thickness of sound concrete, one-sided access. The basic principle, apply a force, look for the echoes in time. You can't see them. If it was metal, it's called pulse echo. You can see those echoes in time because the metal grains are so small, you can use high-frequency waves and get an echo. Concrete grains are large. You can't use high-frequency waves. You can't see the echo in the time domain. So you do frequency domain processing. You take the signal. Phase is what is used in surface waves. I was kind to you as an audience and didn't subject you to phase discussion this morning. I know nobody will thank me for that, but I've tried it before on people and they always go, what? Phase, though, is where we actually get the variation of velocity versus wavelength. There's a lot of technical papers on that if you want to learn about it. But the frequency spectrum is what you may have seen. This is the idea of what's the resonant thickness echo frequency. This is showing two peaks. This would be a flaw and a thickness echo. Okay, here's a project we did recently with combined surface wave and impact echo testing. And it's so recent, I unfortunately don't have a slide of the results. But it was interesting because it showed a very good correlation on this old dam of an interesting phenomena they found. They found out there were zones when they cored it of high-strength concrete and zones of low-strength concrete. I mean like 1,000 psi concrete versus 7,000 psi concrete. When you're doing an earthquake study of a dam with internal walls, there really are internal abutments inside this dam. Here's the spillway. You've got some problems. This shows a cross-section. You can get an idea that it's fairly good size, and you've got a lot of internal beams and walls that are bracing this whole system. Just the access through the galleyways. The testing was interesting. A group that's called Difficult Access, I think, is the name of the company. They're out in Portland. They did the actual testing. We were there recording the data. We trained them down low, and they went and hung up off of this inside of this dam all over. I'm glad they were hanging there, not me. But basically, they're hanging there and tapping and doing the impact echo and surface wave testing. Kind of a rappelling exercise with tie-offs. Thought this was kind of interesting. The human fly. The testing was very successful in that it was correlated with cores to predict strength. We had velocities from surface waves, which was the more reliable test because sometimes the variations of thickness in the walls didn't let the impact echo test give us a good velocity. You can't measure the thickness every place. Problem with impact echo is if the velocity varies, you can't predict the depth of the echo. Surface wave overcomes that by measuring the velocity directly. So we could tell them quality concrete regardless of the thickness of what we were testing. Excellent correlation with strength breaks on cores. It was able to evaluate where there was good and damaged concrete, aiding in their safety analysis of this dam for earthquake loading. The equipment again. This is we can just switch modules and connect up other instruments in this PC. But this is a little impact echo device that's waterproof. You can go tap, tap, tap. We think this is going to be out there. Well, we've already sold them, but it's going to be useful to people where they want to do fast testing. It even works underwater for thickness of slabs and pavements, that type of thing, and walls. Okay, there's just a close-up of that. It's got an electric solenoid that goes tap, tap, tap that's waterproof, and a displacement transducer built in. Okay, let's see. Okay, a few years back, we conceived an idea, and it came about to be a US patent on the idea of impact echo scanning. We've actually used it in one consulting project where there was a need for it. But if you've got smooth enough concrete, we can now scan like a flat slab and profile it for thickness and integrity. This basically just shows tapping, the idea of rolling along, taking data much faster. We got the idea going, and the Bureau of Reclamation said we have a potential application. They have buried precast concrete pipe. It's the so-called, has anyone here ever been involved in repairing pre-stressed concrete cylinder pipe, out of curiosity? One person. This is what their motivation was. There's problems with pre-stressed concrete cylinder pipe sometimes. This is what we like to think of as known damage. So we were calibrating in our research. There's an area down there. Basically, you have a thin steel shell, concrete on the inside and outside of that that's cast at the manufacturer. And then it's wrapped with a wire strand, and a mortar coat of about 3/4 inch to an inch thick is sprayed on it, is typical. Well, what can happen is you can get corrosion of the wires, popping the mortar coat. Of course, all of this pipe is generally buried. So you want to be able to test from the inside out and find in some way, detect that delamination of the mortar coat, that loss of section thickness. And that's what we were doing with impact echo. That's just a close-up of some of the damage. If they'd have given us the contract, we'd still be working to test miles of pipeline. But just tap, tap, tap through a big pipe takes a long time. It's okay to spot check and do that type of testing. But if you're going to look at a whole pipeline, you'd like to eventually be able to scan it. And that's where we were working on the prototype technology to do that. They buried the test pipe later in the research, several sections. We developed, most of our effort went into the transducers. The little red wagon was cheap. So we were just pulling it through there, going tap, tap, tap. We hope for more research to automate this, make an electric vehicle, literally drive through pipelines if the marketplace wants technology like this. We were successful in the transducer development. They're water coupled, goes tap, tap, tap about every 1/3 of a foot, and taking tests 1, 2, 3, 4, going through it as slow walking pace. Just a close-up of a transducer, rolling elements. This shows a sound result, 7.8 inch wall thickness at 8,080 hertz, 0 to 20,000 hertz. This shows a delaminated result that's predicting 6.9 inch wall thickness. The mortar coat has come off and is a thinner section by about 1 inch. When you plot this type of data, this is a short plot, but from 0 to 3 feet, you see that the thickness was over 7.5 inches as we entered this section, and then it dropped into the delaminated zone. So we had good correlation. It worked out well. We were successful in the prototype development. We then made a prototype slab scanner, just unfolded it for pushing along on floor slabs. We applied it on a building on an actual consulting project in Hawaii that we've written about. And we were able to do 23,000 tests of 6,700 square feet in 16 hours of testing time. So we were really moving. But this is an unusual owner that wants to know every third of a square foot, how good is his concrete slab? It was a 4.5 inch thick slab. We've got references and papers on this if you're interested. The reason they wanted to know is the concrete was hitting the acoustic ceiling tiles of the room below. It was quite serious. And they wanted to literally map the cancer, map the problems with those slabs. That just shows using it. We actually tested through a thin asphaltic coating. That worked out well because it was still smooth. When it gets rough, this technology is not yet ready for rough concrete. We tried it and demonstrated it on a bridge deck last summer with the University of Illinois research project for the Illinois DOT. They had a very rough asphalt. We had about a 15% success rate where we could get good echoes and evaluate the soundness of this asphalt overlay deck. That wasn't unexpected. It was a research project. We told them up front, look, if you're willing to help us evaluate it, great. We'll see our problems, but we know where the asphalt's rough, it's not going to work. And that was the case. But it's still, the bridge engineers were quite interested to see this technology, hoping long-term to get a more accurate indication than they get out of ground-penetrating radar and infrared thermography. Just PC-based data acquisition again. Pushing it along water-coupled. Here you can see a close-up of a unit and the water trail behind it. And you can see it was pretty rough surfaces. In some ways, I was surprised it worked as well as it did, to be honest. The ultrasonic pulse velocity method, you can't quite see that, but this is pulse velocity, sending a sound wave through concrete. Semi-direct around the corner, that's direct. Indirect, you don't see very deep. This is really only sensitive the first inch or two. People have used pulse velocity for fire damage evaluation. Surface waves would be and is superior to pulse velocity for fire damage evaluation because it shows you the variation versus depth, whereas pulse velocity is a refraction phenomena and not as accurate. The basic test, sending and receiving, grease coupled, checking this bridge column for some void. It had been buried for years. They dug it up and they had surface void exposed. So they got concerned about interior void. The unseen defect. PC-based recording, a live signal. This is on a parking structure precast at Dallas-Fort Worth Airport, looking at quality assurance of epoxy injection. Testing through this beam and across diagonally this crack, and then comparing diagonally through sound concrete. It was really only a hairline crack, very tight. Before injection, almost no signal. The meter was misleading. If you just used the straight meter, it said 84 microseconds. In reality, the signal's out here. It's very slow, just an open crack by testing diagonally across it. This shows after injection, much better signal 1 day later, 14,000 feet per second. That compares to 14,500 in an uncracked section. Quality assurance of the fill in this case. You can do quality assurance of epoxy injection repairs and other repairs with any of the three methods I've talked about so far. There's advantages, plus and minuses to each of them. We've done a little work on scanning, mostly in research. The idea of a fixed receiver and moving a source. This is a research project we did for National Science Foundation, some small business research, to try and image built-in flaws in concrete. These are voids. We found these the best. Styrofoam blocks. We didn't do so well at these, partly because while occasionally a contractor is able to build a perfect defect, we didn't. These little Ziploc bags were supposed to simulate an open crack completely filled with air. We should have vulcanized them or used really heavy rubber because they became tightly closed cracks as soon as the concrete hit them. It really takes a little talent to build the perfect defect. You probably didn't think that. This one really collapsed. We cast some honeycomb concrete blocks, and then we did the testing. Prior to this research, a School of Mines professor had done some work simulating tunnels for tunnel detection over in Korea for the military, And he actually took 2 weeks of a graduate student's time to get the data from one set, one line. And I thought I had a bad professor in college, I tell you. No, I really didn't. I had an excellent professor, but he liked to work hard too. But we couldn't afford that. So we managed to come up with a scanning source that moved and clicked, water coupled, and we could get the same amount of data with a single receiver on the back in an hour and a half. I think if this technology becomes popular, we'll use multiple receivers, and it'll get the actual data acquisition time down under half an hour, maybe even 15 minutes. But again, most people don't necessarily need to see internal conditions in concrete with a tomogram. They might be happy with the impact echo, surface waves, or pulse velocity. But I wanted you to know the technology now exists. This shows a scan from 0 to 4 feet. This is the energy of the signal. This is the time of the signal, and the receiver was about in the middle. Longer time, lower energy. You can see the reverse curvature. This actually was an anomaly down in here, showing some low energy and a little interruption in the time. This is an image. The yellow and red show the slow velocity concrete. You can see we got some indication here of the voids. This is what it looked like if it had been straight through. This is after all the angles were shot. Because tomography basically means that we had that receiver at 38 different locations on the backside as we moved the source, clicking 38 times up this way. So you have almost 1,600 pieces of data that are analyzed to produce this image. So it's quite a bit of data. This shows straight through testing, and this is more technical ray density. The data is least reliable at the top and bottom because you have the least data there. This one showed the defects but smeared them. That's with some of those collapsed bags. This showed not very good at all. It was a very minor defect, and now it got confusing. We think if we can do amplitude tomography, the energy of the signal, we did a little research on that, as well as velocity, that this technology could someday, with some investment and research funding, start to look almost as good as they do in medicine. But it's a more difficult material to test than the human body. And so far, I haven't seen anyone as worried about cutting and coring into concrete as they are the human body. Okay, the conclusions. It was practical because scanning makes it a lot faster. It worked best on the voids, good to fair characterization of honeycomb cracks and weak concrete. Okay, how many people here have ever had to do underwater repairs? 1, 2, 3, 4. On foundation elements and walls, that type of thing? Okay. I decided to show this one. We do a lot of quality assurance of new concrete placement in drilled shaft foundations for bridges because it's underwater concrete placement. They cast in place access tubes, and we do basically ultrasonic pulse velocity testing between these water-filled tubes. That's what's called cross-hole sonic logging. The parallel seismic we normally do for unknown foundation depths. How deep is the foundation using a boring? But this application was on an existing foundation. They knew how deep it was, but there was a concern over cracking. It's in the south of Korea. You've got 4 piles, cast-in-place concrete pilings, under each one of these to 5 piles. I'll never forget sitting in a little cafe, and an 80-year-old Korean man asked me through the translator, "Why does this 1909 Japanese bridge working great and our 7-year-old new Korean bridge falling down?" That's the way he put it. The answer is, probably was well built, but the answer is they had taken heavily loaded steel trucks and literally failed the superstructure of the bridge in 7 years. They didn't pay any attention to load limits. They just tore it apart. But when they were taking off the superstructure, it's kind of missing back here, they discovered, and a TV crew came out, the world all over has TV crews, and they discovered there were all kinds of cracks in the exposed piles when the tide went out. So now there was a concern. Were these pilings cracked all the way down? So we got out there and doing our testing, and the tide basically oscillated here to here. They had drilled through and put slope inclinometer casing 10 to 20 centimeters down through the water in the soils and down about a total depth, I think, on the order of 70 or 80 feet, if I recall correctly. And we were going to test with parallel seismic and cross-hole sonic logging between these tubes. They had tubes on opposite sides, sometimes 2 tubes, sometimes 4 tubes, and we were testing and sending the wave through the water, through the concrete. Where normally we would have tubes inside of a concrete foundation for quality assurance testing, you can put them outside. It works very well in the water zone because you get perfect coupling through water. If the sediments are fully saturated, it works well too. If they have any gas in them, then you lose the signal, as you'll see. But this was doing the parallel seismic testing, hitting the top, an instrumented hammer to send the wave down. What did we see? This is depth, 0 to 14 meters, time, 0 to 5. Very good data, just showing the velocity of concrete, 4,200 meters per second. Zip, zip, zip. Had there been a break or poor quality, we'd have seen a step to the right and a loss of signal. This shows the amplitude of the signal. In the water zone, it was very high. Then it dropped in this zone of the soils, and then it got higher again in the soils. But always good signal arrival. The sonic logging, we dropped 2 probes, 1 in each hole, and pulled them over this depth wheel, and checking automatically about every 2/10 of a foot. You can do a sonic log in 5 minutes on 100 feet, no problem. And you've just taken 500 measurements of the speed of sound between the 2 tubes, which are through the pile cap here. This showed excellent signal in the water zone. The tubes wandered, so it took longer, uniform energy versus depth. And then we had some signal in the soils, but we also had a lot of zones where we lost it. This was correlating with the loss of amplitude in parallel seismic. Gaseous sediments, silts, were actually not fully saturated, attenuating the signal. The combination of the 2 tests led to the conclusion that the foundations were sound. The problem was this. They did a very unusual construction technique, almost like a caisson. They sunk a heavy casing all the way down, inch-thick casing, greased the inside of it, excavated the soils out, of course, filled it with concrete, and at 12 to 24 hours of age, they pulled that casing off the concrete to reuse the casing. And it didn't always come off easy, so they racked it at the top and cracked it. That was what happened. Steel was expensive. They didn't want to lose it. Impulse response. I think I have enough time to get through this. This is the idea. How many people here are involved in slab jacking, mud jacking? Anybody? One person, a couple people. This is looking for voids. You can do it outside of a concrete slab on grade or pavement. You can do it for a conduit of a dam, looking outside of tunnel linings, that type of thing. Looking for voids, loss of subgrade support. Hitting with an instrumented hammer, measuring with a geophone. This is testing a subdivision pavement with some problems. Hammer and a geophone. This was a big problem. We, a lot of times, are working around sprinkler systems. One of 2 things have happened. A lot of times the bolts have corroded through or the pipe has corroded. I really think if I ever owned a big building, my sprinkler would be outside in a little building and I would ruin my parking lot. I've seen enough of these failures, that's what I'd ruin. But these bolts had corroded through, came apart at night, of course. 120 psi water pressure in an 8-inch line will do things. This was in Dallas. It had 3-foot deep grade beams going down to keep the nasty moisture away from the expansive soils. They were all throughout this site. Well, it acted like a piston. It just confined the water, up came the slab. Looking down into the pit, and it ran for 4 hours before they could turn it off. They had 2 feet of water. This shows heavily loaded slab. These are bearings, very heavily loaded slab. That slab, this is a 6-inch ruler, a 6-inch diameter steel pipe column, painted. It lost 17 inches of paint because the slab floated 17 inches. It cracked at the edges. It was welded wire fabric reinforced, cracked about 6 foot in, but held together, crowned very nicely. The building general manager said when he walked in, he thought the roof had come down. No, the floor had come up. So it's just amazing. But once the water was shut off, all that slab load pushed the water out. Now the question became, what support did they have? And that's where we came into it. We sounded it off on about an 8-foot grid. We typically test on 5 to 10-foot grids, sort of like slab jacking, to define the area of support. We can't tell how thick the void is with this test, but we're very sensitive to the degree of support because we're measuring stiffness. So you measure the force applied with that instrumented hammer, you measure the vibration response, then you process it. A void will have a higher vibration per pound force and more irregular shape versus good support. Less vibration per pound force and stiffer at the low frequencies. So it's just a way to quantify what you all know. This shows before grouting, it was actually quality assurance as well, and after grouting, changing the stiffness from 170 kips per inch to 500 kips per inch and smoother. We had excellent correlation. Works very well on 6 to 12 inch slabs, 4 to 12 inch slabs. You can do it up to 2 feet, but you have to be very careful as the slab gets thicker because it gets to dominate the response just because of the thickness of the concrete. I think that concludes my talk. I sure would be happy to answer any questions. Yes, sir.
Considering that the velocity through the concrete is a function of the porosity of the concrete, have you tried quantifying the moisture content or variations in the moisture content in a concrete slab? The reason I ask is we are using GPR to do that, and we're getting very good results. So I was wondering, if this sonic method could be used for that.
There's a slight relationship of velocity and whether a concrete is saturated or not. But I wouldn't recommend using it for what you described. I think the radar is a better technique. There's also some dielectric basic measurements.
That's exactly what we're doing.
Yeah.
Percometer, yeah.
Yeah. Okay. And there was a question here? Yes, sir.
Surface wave testing, I believe you said you have to have a pretty smooth surface for that to work.
No, that's actually on impact echo scanning.
Impact echo.
Surface wave testing, you can always grind a concrete if it's that rough, but normally use that new bar is surprisingly good at working on rough concrete, but extremely rough you can use accelerometers and little washers and grease mount them, and then they magnetically attach the transducers and normally deal with rough concrete. Now if it looks like exposed aggregate terrazzo finish, it gets harder. But
That's what I was wondering, how rough is rough?
we've never found a concrete surface we couldn't test with the stationary tests. The scanning's a different story because you start bouncing and you don't get the coupling, but a stationary point we've been able to test. Okay. I guess the answer to how rough is when you cannot get any even vertical base at all. There can be too rough. I remember some finishing where they just left the excess concrete all over it, and that had to be ground. Okay. Any other questions? Okay.
Where you were doing your cross pull tomography on the piles where you had the inclinometer cables
Yes.
on the outside casings, what is the importance of that casing being in contact with the concrete all the way?
It was not in contact. If it's water coupled, it's not critical as long as you can tell a gradual change in shape like it showed, and that just showed the tube was not as close to the concrete.
So what kind of variation do you have?
Well, in that case, I think it was 10 to 20 centimeter variation, about 4 to 8 inch variation. Obviously, you want them as vertical as possible. When we've done it on a New York DOT project off of Long Island, instead of having divers go underwater to do very slow testing, they put these tubes down, and we were able to do it very fast and much more economical. They strapped them on, literally. They were able to tie them on. You might want to use, if you have current, steel tubes as opposed to plastic, so they don't get swept in the current to be stiffer. But it's a technique, I think, that can replace some diving and give you more detailed information faster. Okay. Thanks for everybody's patience in being subjected to all that many slides. Have a good day.